Okay, so this is going to be moving right along, and we are going to do sections 4.3 and 4.4 at the same time. This is from the notes posted to Blackboard. So what we just finished doing in 4.2 was talking about the unit circle, radians as a new way to do measurements for angles, some types of problems that become immensely easier when you switch to radians. But now we have to get to the tri part of trigonometry, which is talking about triangles. So we should get some terminology out of the way. So if we have a right triangle, as such, we denote which angle is the 90-degree one by, this is way too small. We denote the angle, which is 90 degrees, by putting a little square in it to remind us that it's a square angle or a right angle. We also say that the two side lengths which are connected to the 90-degree angle are called legs. So sides, I'm going to say touching the right angle are called legs of the triangle. So this would be one leg and this would be the other leg. And the remaining one is the hypotenuse. And so if we label these three sides, it's pretty usual to call them A, B, and C. Then by the Pythagorean theorem, we know how to derive the lengths of the remaining third from any given two, right? So we see that C is going to be the square root of A squared plus B squared, which just comes directly from the Pythagorean theorem. We have that A is going to be the square root of C squared minus B squared, and B is equal to the square root of C squared minus A squared. So if you know any two side lengths of a triangle, then just using the Pythagorean theorem, you can figure out the remaining side length like this. We also go ahead and have a standardization where we talk about the angle of a triangle. We always sort of put it on the bottom, right? So I wouldn't really talk about this one. I totally could. I would just first rotate it so that it's on the bottom. And we'll see why in just a minute. But we call this angle theta, like we did in the previous section. And that's pretty much that. So the terminology out of the way, we have the legs of a triangle, which are the ones that form the 90-degree angle. We call the angle in question theta, sometimes alpha. If there's more than one, we'd use like alpha and beta. And we call the longest side, and it is always true that the longest side of a right triangle will be the one opposite the 90-degree angle. We call this longest side the hypotenuse. So we can now, one thing that ancient mathematicians, and when I say ancient, I do mean fairly ancient, like as old as Euclid or possibly even Pythagoras himself, we believe that this sort of information has been known by the ancient Mesopotamians, by Sumerians, by all kinds of different civilizations. But we say, if you look at this right triangle or this right triangle or this right triangle, or pretty much, well, it is every single right triangle, the following relationships will be the same. So if we just take this one, for example, and we have A, B, and C, where C is always the hypotenuse, then I can say that the ratio of this side to this side is not always the same, but it is directly related to this angle. So again, I'm going to call this angle theta. And so we say that for a given triangle, like this one, where it has some side lengths, the ratio of any two of those side lengths can be expressed as some kind of manipulation of this angle. And that's not immediately obvious. Of course, in modern time, modern mathematics, we've known this for a very long time, so it does seem fairly natural. But at first glance, or first introduction, the idea that the side length, or rather the ratio of the side lengths of a triangle are related directly to the angle measure of only one of the internal angles is non-trivial. It kind of comes out of nowhere. And as I said in the notes, there has been a long and tired history of figuring out these relationships. But for right now, for you and me, and because they exist in the modern time, it's just a button on a calculator, we can say that the ratio, so if we are talking about this triangle, and with respect to this angle, then I can say the ratio of A over C, I'm going to call that the sine of theta. Likewise, I'm going to say B over C is going to be the cosine of theta, abbreviated to sin and cos, but pronounced sine and cosine. Obviously, I could also take the reciprocal of this and have the ratio of C over A, and that should give me exactly 1 over sine. And in fact, that's actually called the secant function, but because sort of the reciprocals are defined in terms of sine and cosine, we don't really bother with them that much. The last one that we might want to talk about is the ratio of A over B. And this one we call the tangent of theta, abbreviated to tan. Can you see all that? Yeah. And so it was noticed in antiquity, and it is definitely true, that for a given triangle, no matter how you scale it or stretch it, as long as it's a similar triangle to the one you started with, the ratio of the side lengths can be expressed as some kind of function of just one of the angles. And so these are the definitions. And it's not, like right now they kind of just look like, all right, it's that one over C, or it's that one over C, or if that one doesn't even have C in it. It might be a little confusing and definitely hard to remember which one is which. And so because of that, at least this probably was not used in antiquity, but it definitely has been used for modern math teachers, the mnemonic SOHCAHTOA, which I always think sounds like some kind of Pacific Islander chant for something. But this is an acronym for sine is opposite over hypotenuse. This one is an acronym for cosine is adjacent, not a G, adjacent over, I'll just abbreviate hypo, and this one is tangent is adjacent over opposite. And so what does this mean? Well, it means that if you have a given angle of your triangle, then there's going to be one leg which is adjacent to that angle, meaning it forms part of that angle, and there will be another leg which has absolutely nothing to do with that angle. It's actually opposite the triangle from it. So we call the leg that is connected to the angle adjacent, and the leg which is opposite the angle opposite. Note that we can perfectly disambiguously refer to these things because the hypotenuse, while it is also adjacent to this angle, is not one of the legs. So by talking about the legs, we can unambiguously refer to these things for any triangle. So another way to do this would be to see that sine is going to be, well, it's A over C. A is the opposite leg, and C is obviously the hypotenuse. So this is opposite over hypotenuse, which is exactly what we have here in the mnemonic. Likewise, cosine is the adjacent leg over the hypotenuse. So this is going to be adj over hype. And tangent is adjacent over opposite, so it's going to be, oh, I'm sorry, TOA, it should be opposite over adjacent. See, even when you remember them, you can still misremember them. So this is opposite over adjacent, and so we see that A over B is indeed the opposite leg over the adjacent leg with regards to this angle. So this is indeed op over edge. And so I personally have found this to be immensely useful. I do not bother memorizing which leg or whatever goes where. Instead, I just remember so ka toa. And so it's this beautiful little mnemonic that helps you remember them super easily. We also, I alluded to it before, so the ratio of side lengths for a right triangle is how we define sine, cosine, and tangent. But if you wanted to find what is the ratio of b over a, that's not covered by one of the three trig functions we've talked about so far. Instead, we can notice that this is 1 over a over b, which seems a little contrived, but it is. This is contrived because we get 1 over a over b, but we know a over b is just tangent, right? It's opposite over adjacent. So this should be 1 over tangent, just by plugging in tangent for what we know it's equal to. And we call this thing, this sort of inverse ratio of the side lengths, we call this the cotangent. We'll just put it here. This is cotangent, abbreviated as cot of theta. But this is, we remember this is just 1 over tangent of theta. It's the cotangent. Now, that thinking is going to be broken in just a second, but in normal, at least the way we would hope things work, is the co-version of something is 1 over it. Like I said, that is not the case because whoever invented these names did so with your best interest nowhere in their mind. So, 1 over tangent is called tangent. If we do c over a, well, this is the same as 1 over a over c. We know a over c is opposite over hypotenuse. It's the sine. So this is 1 over sine theta. However, we immediately run into a problem because I cannot call this function a cosine because we actually already have cosine, and it's not 1 over sine. So instead, this one gets the name cosecant of theta. And I'm introducing them in this order because I want you to understand that the naming convention of these things is not what you should be using to remember them. Because if you go by, oh, cosine is 1 over sine, cotangent is 1 over tangent, cosecant is 1 over secant, you would get everything wrong. That's just not the way it works. I wish it was, seriously, wish it did, but that's just not the case. And of course this leaves us the other one, which is c over b, which is 1 over b over c, which is of course 1 over cosine of theta, and this is secant of theta. So yes, 1 over cosine is secant, and 1 over sine is cosecant. It doesn't make any sense to me either. But this is just the naming convention, and if you actually look on your calculator, you will see that there are buttons for cosine, sine, and tangent, as well as cotangent, cosecant, and secant. And so, in certain circumstances, where all you know is the ratio one way, you can figure out the ratio the other way by taking the inverse. Okay. Alright, so now we should look at the unit circle again. Because as I hinted at the beginning of the notes for this section, trigonometry is really the study of three main things. It's the study of cyclic behavior called periodic motion, it's the study of circles, and it's the study of right triangles. And those things seem, at least, no pun intended, tangentially related. They actually are very, very deeply related. And they're all related by the Pythagorean theorem, which is very nice. So if we look at the unit circle on the xy axis, and we give it a radius of 1, again, that makes this the point 1, 0. That makes this the point 0, 1. Makes this the point negative 1, 0, and makes this the point 0, negative 1, right? Just by going on what we know about the Cartesian coordinate system. Since this is length of 1, we'll find that if we pick some angle here, like if we pick pi over 4, then when we draw this line, we have this line is the radius of the circle, because all the lines emanating from the center will be. And so we know this also has length 1. Just so we're not confused, I'll erase that one. And then we can also see that the coordinate points for this point, right? So this forms an angle of theta equals pi over 4. And the point that is intersected on the unit circle by this angle, again, always measured from the positive x-axis, this point is going to have some x and y as its coordinates. And the whole point of sine and cosine and tangent are figuring out what are those coordinates. And another really, really nice feature about the unit circle is because this is a length of 1, if we say, what is the sine, or, well, first, I think we would all agree that this line is the y value, right? So if this is 0, 0, then this is exactly the y value for the point, for the coordinates of this point. Likewise, this distance down here is the x value. And that's just because we set the center of the circle at the origin, so this is exactly its distance x away, and this is exactly its distance y away from the origin. And so these two coordinates actually wind up being the lengths of these two sides of a triangle. And because the Cartesian coordinates are perpendicular to each other, we get, just from this angle and this circle, we get this right triangle. And so we can now say, all right, what is the x value of this triangle? Like, what exactly are those coordinates? And so if we look at this, we can say, let's do sine first. So what is the sine of pi over 4? Given this triangle, and this is the angle theta. Well, based on our definition, right, so katoa, soa is going to be sine is opposite over hypotenuse. So this is our angle. Which side is opposite? It's going to be this one. And this is length y. So this is going to be y over the hypotenuse, which is 1. And so we find that the sine of pi over 4 is actually exactly equal to the y value of the position that makes that angle. This is one of the other things that's super nice and elegant and simple about using a unit circle to talk about trigonometry. Because the radius is length 1, and it's always the hypotenuse of these right triangles, it means that the side lengths of the right triangle produced by the angle are just the sine and the cosine. Because if we look at the cosine of pi over 4, if we remember, so ka is cosine adjacent over hypotenuse. The adjacent side length to this angle is x, and the hypotenuse is once again 1. So we see that we can rewrite these coordinates as the cosine of theta, or I guess in this case, since we actually know what theta is, I should put it in, pi over 4. And the y coordinate is the sine of pi over 4. And that comes from the properties of the Cartesian coordinate system and the definition of sine and cosine. So we have an angle, which defines a point on the unit circle. The distance in the x and y direction of that point give us a right triangle. And because the hypotenuse is length 1, we actually know that these lengths are going to be exactly the sine of that angle and the cosine of that angle. And then what's left is to geometrically figure out what these distances have to be. So when it comes to this one, because this is pi over 4, we can use that we know the internal angles of a triangle have to sum to 180, which is pi radians. This is 90 degrees, which is pi over 2. This is obviously pi over 4 because we've made it so. So what does this remaining angle have to be? Well, it's going to be pi minus pi over 2 minus pi over 4, right? We need everything to sum to pi. We have pi over 2 and we have pi over 4. So taking those away from pi should give us what the last angle has to be. And if we do this, we get that this is going to be 4 pi over 4 minus 2 pi over 4 minus pi over 4, just to get everything into the same denominator, and this is going to be pi over 4. So it turns out that if this angle is pi over 4, then so is this one, which makes sense because if we have the 45, 45, 90 triangle, these happen to be the exact same triangle, right? Because we have 90, pi over 4 is the same as 45 degrees, and pi over 4, which is the same as 45 degrees. So these are actually the same triangle. We just know on the unit circle, the hypotenuse is length 1. If we look at the 45, 45, 90 triangle, we can figure out some things about it. So I don't want to be super cluttered, but I don't really want to erase anything I have up. If I draw a square with side length 1, and I draw a diagonal of this square, what is, well, first of all, it creates our 45, 45, 90 triangle, right? Because this is half of 90, so it's 45, and so we get this. What is going to be this length? Well, we can bring in good old Pythagoras again and say we know that 1 squared plus 1 squared has to equal x squared. What this is this is just 1 plus 1, so this is 2 equals x squared, and so we get that x equals the square root of 2. Technically, it should equal the positive or negative square root of 2, but since we can't have negative lengths, then we're going to go with the positive version. So, if this is square root of 2, then we know, well, we don't really know much right now because this is for a triangle with leg lengths 1 and 1, but this is a triangle with hypotenuse length 1. So, another thing that this diagram tells us is because these two angles are the same, is these are actually the same value. A value I'm just going to label d for distance. And so by the Pythagorean theorem here, we have d squared plus d squared equals 1 squared, right? And by our intuition gained from looking at the square and figuring out the diagonal, we can do the same thing here. D squared plus d squared, well, that's just 2 d squareds. So this is 2d squared equals, and 1 squared is just 1. So now, to figure out what d is, we can say that this is d squared is equal to 1 over 2 by dividing by 2 on each side. And lastly, we get that d is equal to the square root of 1/2. So we come here and we say geometrically, given that we know the rules of a right triangle and given that the hypotenuse is length 1, we have figured out that this side length is 1 over 2. And because this is the same as this, we get that this one is also square root of 1 over 2. And you might think, okay, cool, now we know that. What does that give for us, though? Well, it actually gives us quite a lot, because we also know that these two lengths give us the coordinate values. And before, we figured out that the coordinate values are exactly the cosine and sine of that angle. So now we've combined the definition of sine and cosine to get that it is the coordinate pair, and we used geometry and the Pythagorean theorem to figure out what those values actually are. And so we can say that this coordinate point should be the square root of 1 over 2 by the square root of 1 over 2. And this gives us that the sine of pi over 4, which is again just the y value here, is exactly the square root of 1 over 2. Likewise, the cosine of pi over 4, being this length, is also square root of 1 over 2. And so at the end of this process, we took an angle, we looked at how the definition of sine and cosine tell us that the coordinate points, or the coordinate pair for this point, is just going to be the sine and cosine of that angle, and then geometrically we found what those side lengths actually are, which gave us what the cosine and sine of that angle is. And you can do the exact same thing using, well, I don't want to erase it, but I suppose I have to. If I quickly redraw pretty much everything I just had. We have unit circle, and if I create this angle, and let's say that this is pi over 6, then it also generates a point on the unit circle, and by dropping this altitude we get a right triangle where, again, this is the x value and this is the y value of this point. And we can do the reverse conversion to figure out what is pi over 6 in degrees, and it turns out it is 30 degrees. So this is 30 degrees. Now, some of us may actually know this, others it may be new to, but there is a fairly well-known triangle identity called the 30, 60, 90 rule, which says if you call this side length x, then the hypotenuse will be 2x, and this leg will be root 3 times x. Where did that come from? Well, just as we used this square to figure out the 45, 45, 90 triangle, we can use the equilateral triangle to figure out the 30, 60, 90. If we take this and then we cut it in half, we see that this makes a right angle, and we know, since this is an equilateral triangle, that this is 60, and we cut this in half, so this has to be 30. If we have a side length of 1 everywhere, this thing becomes a side length of 1/2, since we just cut it in half, and we have to solve, again using the Pythagorean theorem, what is the height of this triangle, and when you do that, you get that it's exactly root 3. Since triangles scale very nicely, then this is the same for whatever x value you start with. We see that the hypotenuse of this triangle is indeed 2 times the shortest leg, and the height of the triangle, completely blanked on the word, the height of this triangle is going to be root 3 over 2, my bad. What this gives us, though, is that we can take this triangle identity, which comes from the geometry of an equilateral triangle, and apply it here, because this is the angle 30 that forces this to be the angle 60, and we have a 30, 60, 90 triangle. Then we can see by this, since our hypotenuse is again a radius of our unit circle, then this value, 2x, equals 1, which means x has to be 1/2. I used x here even though it doesn't actually line up with this. They're kind of separate diagrams. But what this gives us is that the shortest side of the 30, 60, 90 triangle has to be side length 1/2 if the hypotenuse is 1, which it is. So I can now replace this y with 1/2, and just as with the other thing, we can say that this x value has to be √3/2, because it's the other side in the 30, 60, 90 right triangle. This gives us a coordinate pair of √3/2 and 1/2, but we know that this is also, by the same reasoning as before, the cosine of pi/6 and the sine of pi/6. And so we get the next equality, which is, oh, can you even see that? I don't think you can. That sine pi/6 equals the y value, because that's where they line up, which is 1/2, and the cosine of pi/6 equals the x value, which is √3/2. And so just with these two examples, we have found 45 degrees and we found 30 degrees. Also, if we were to do this triangle, which corresponds to an angle of 60 degrees, or pi/3, then we could do the exact same thing. It's just this triangle sort of flipped like that. Same is true if we did this angle, which is 45 degrees there. Oh, video auto started. I'm just going to talk over it. If this is also 45 degrees, then we can figure out pretty easily from the past one that we just did what these coordinates have to be as well. It's going to turn out that it's going to be the negative square root of 1/2 by the square root of 1/2, because it's the same height, but it's on the opposite side on the x-axis, so it has to take a negative value. I'm about to run out of battery, so I suppose I will pick up with the rest of 4.3 and 4.4 in just a second. Okay, sorry about that. So we just concluded with figuring out how to come up with the sine and cosine of pi/6, and just before that we did the sine and cosine of pi/4. I just briefly mentioned that we can do the exact same thing for pi/3, because pi/3 converted into degrees is going to be 60 degrees, and so we actually wind up with the same 30, 60, 90 triangle, just with it rotated. So we got √3/2, comma 1/2, and at pi/3, it's going to be the exact same thing, just now the x value is the short leg and the y value is the long one. So it's going to be the exact same pair, just flipped. So this is going to be 1/2 by √3/2. So we can use the Pythagorean theorem and geometry to come up with some known values for sine and cosine, and we can actually extemporize quite a bit more from that. But let's just do a couple of examples. Okay, so the first one from the notes says, find the cosine of 2π/6. So for this, the first step is always check if it's in simplest form. And it turns out that it's not, right? So 2π/6 is going to be the same as pi/3. Right? Since 6 is divisible by 2, so we get some cancellation. Then we can look at the unit circle to see that, well, I actually just covered it. When we do pi/3, we wind up with a 60, 30, 90 triangle, and so we get the exact same ratio of the side lengths. So we get x, 2x, and √3, √3x. And so in our case, since the hypotenuse in the unit circle is always the radius, which is unit 1, then we get that this is 1, which makes this 1/2, which makes this √3/2. So we can use this because then we know that the cosine of an angle is always the x value when we plug it into the unit circle. And so we get that this is going to be 1/2. The next one says, the next one says, find the y value for the point which forms theta equals 420 degrees. Right, so I kind of paraphrased what I have exactly in the notes, but the point is that we can use the unit circle and these known values for sine and cosine to figure out what this is. In section 4.2, we used this exact one, so we actually know that this one turns into, no, it wasn't that one. It was, which one was this? 7 pi over 6, right? That's what we found that it was by converting it from degrees to radians. So we know it's this. However, we know that that's more than 2 pi, and so this is going to be sort of equivalent to just pi over 6 when we take away 2 pi from it. Oh, I'm sorry, no. 7 pi over 3, that's what it was. My bad. So yeah, 420 degrees, when we convert that into radians, we get it's 420 over 360, which is going to be the same as 7 over 6. Oh, so I guess it was 7/6. 7/6. And then when we multiply that by 2 pi, we get 7 pi over 3. So it was over 3. All right. This is why I'm checking it, is because I couldn't remember. So we get an angle of 7 pi over 3, and then we subtract from that 2 pi, but 2 pi with a denominator of 3 has to look like 6 pi over 3, and this gives us pi over 3. So that's just, right then I kind of blanked mentally on exactly what we had said that this was, but you can see it's actually really quick to just figure it out again from scratch. So we get 420 degrees is sort of equivalent on the unit circle to pi over 3, and it's looking for the y value. So we have this triangle where this is pi over 3. We know the hypotenuse is length 1. Since this is, again, the 30, 60, 90 triangle, I know this has to be length 1/2, and this has to be root 3 over 2. And when it says find the y value, it simply means finding the vertical leg of that triangle. And so this happens to be root 3 over 2, and so that's our answer. These two questions basically amount to what are the x and y values when we have pi over 3, but phrased differently and with different steps. The next example is, sorry, we bought the wrong paper, so these are very thick. Right, so the next one says find the sum of the, was it x? Yeah. X coordinates for theta equals 2 pi over 3 and then 5 pi over 4. So we notice that, well, this is some multiple of pi over 3. It's 2 of them. So I know on the unit circle, if this is pi over 3, and that gave us a coordinate of 1/2 by root 3 over 2, then when I do 2 of them, I'm going to get over here, and while this is the angle 2 pi over 3, this is still the same 30, 60, 90 triangle. And since it's in the exact same orientation as this one, we see that it's going to have nearly the exact same coordinates. So if this is length 1/2, and this is the same structure as this, just reflected over, then this length is also 1/2. But because we're talking about the coordinates, it has to be negative 1/2. Or rather, the length is 1/2, but the coordinate is negative 1/2 because it's on the negative side on the x-axis. And then, same thing here, we have that the y value, which is the vertical length, is root 3 over 2, but because we're still on the positive y-axis, this is going to remain positive root 3 over 2. Since it's looking for the sum of the x values, I know that for this one, we get x equals negative 1/2. Now for the next angle, 5 pi over 4, this is also going to be a multiple of pi over 4. And so we know that for pi over 4, we have values root 1/2 by root 1/2. And when we do 2 of them, we get to pi over 2. When we do 3 of them, we go there, 4, 5. So it's this coordinate pair that we're looking for, and specifically looking for the x value in. Since this is positive, and they're always the same, we know these are also going to be the same, but since it's in quadrant 3, we know that it's in both the negative x-axis and the negative y-axis. So it's going to be the exact same values, just both negative. I hope you can read that. And then the question says, what is the sum of their x coordinates? So this one gave x equals negative square root of 1/2. So I'm going to do a little step here that I do in the notes earlier, but I didn't do before because I kind of skipped over it. On the regular unit circle, or almost any unit circle that you find on the internet or are presented in a textbook, you're not going to see pi over 4 written as cosine of pi over 4 equals the square root of 1/2, or the sine of pi over 4 equals square root of 1/2. You're actually not going to see it in this form. You're going to see it as root 2 over 2. And the reasoning is given in the notes, but just suffice it to say that they are the same expression. Square root of 1/2 is the same as root 2 over 2. So, when we go to have this sum, which the question is asking for, we have to do negative 1/2 plus negative root 1/2, but I know this is just going to be the same as negative root 2 over 2. Now, this is going to be really easy. We have negative 1/2 minus root 2 over 2, and so this is going to be negative 1 minus root 2 all over 2, or the way I give it in the notes at the very end is the final answer of negative 1 plus root 2 over 2. And that's just because when you distribute this negative 1 into there, you get the right answer. So that was that example. Yeah, okay, so now we're going to do some more stuff that isn't just straight up using these known sine and cosine values, but instead using more the definition of sine and cosine as triangle ratios, or the ratios of the side lengths of a triangle. And so if we say we have sine of pi over 6 equals 4 over x, we want to solve for x. And it's a general trend in mathematics in general, but also in engineering and probably anything else that humans have to think about. The first step should always be draw a picture. And in math, especially trigonometry, that is of the utmost importance. So we know we have the sine of pi over 6. We also know the sine of an angle is so kato. So it's soa, it's opposite over hypotenuse. So what this is telling us is in a triangle with this angle, pi over 6, it's telling us that the opposite side length has length 4. And that the hypotenuse has length x. Right? And so this is how you would translate this equation into a particular triangle. And so now we can look at this and we can say, well, what does x have to be? Well, we could use the triangle, we could try to figure things out using Pythagoras or something like that, but we actually already know what the sine of pi over 6 is, right? Using the unit circle, the sine of pi over 6 is exactly 1/2, right? We just go to pi over 6, look at the y coordinate, because that's what the sine is. Cosine gives you the x value, sine gives you the y value. So we have this relationship. And this is actually going to be really easy to solve. We're just going to do multiply x on both sides, and then multiply 2 on both sides. And we get that x equals 8. And that's the answer for this question. For the next one, it says, find all side lengths. So, if I say we have sine of theta, so in this case we don't know what the angle is, sine theta equals 3/5. Well, again, if we remember the definition of sine, it's opposite over hypotenuse. So if we draw our angle theta here, what this is telling us is the opposite side to this angle has length 3. And the hypotenuse has length 5. So again, this is how you take an equation using trig functions and translate it into a triangle, where then we can use geometric means to solve this. So we basically know 2 of the 3 side lengths, and so the last thing we have to solve for is the third length. Using the Pythagorean theorem, we know that 3 squared plus x squared has to equal 5 squared. Or x has to be the square root of 5 squared minus 3 squared. And again, this is like from the beginning of this lecture, when we say if you know the side lengths of any 2 sides of a triangle, you can figure out the third. This is going to be the square root of, well, 5 squared is 25, and 3 squared is 9. So we need to, all right, what's 25 minus 9? It's 16. So this is the square root of 16, which of course we know is 4. Again, technically it's supposed to be the positive or negative 4, but we know distances can't be negative. So we get that the sides are 3, 4, 5. And in fact, it's not every case, but if you see a triangle with side lengths 3 and 4, or 3 and 5, or 4 and 5, or 3 and 5, or whatever the combination, it's probably going to wind up being the 3, 4, 5 right triangle, because it's just a very, very nice, simple, well-known triangle. If you take a side length of 3 and 4, it gives you a hypotenuse of 5. In fact, in ancient Egypt, when they were building the pyramids, they actually used this fact to construct a right angle. They took sticks with sort of a unit, and they had one that was 3 units long, one that was 4 units long, and one that was 5 units long, and they built a triangle out of it, and that forces the one part of that triangle to be a right angle. So it's a way to create a right angle sort of out of nothing. Like if you don't have a ruler or a compass or anything, like if you just have sticks, you can still make a right angle and of course build the pyramids, because no aliens were involved. Yeah. Alright, right. So for this next one, I think it's the last example from section 4.3. So this one says that you are, so this is going to be you, so you are 10 feet away from a cliff, and the cliff stands at some height, right? It has some height to it. And you know that the angle that's formed from where you're looking to the top of the cliff is exactly 30 degrees. Oh, also, just for this example, you happen to be exactly 1 foot tall, just because. And the question is obviously find the height of the cliff. If you know your height, your distance to the base of the cliff, and the angle that it makes to the top of the cliff, you should be able to figure this out. So the first step is convert 30 degrees into radians. This is going to be, again, our good friend pi over 6. And we now know that the sine of pi over 6 is going to be, oh sorry, no, we don't want to use sine in this case, that's right. For this example, because we don't know the hypotenuse, and sine and cosine both use ratios with the hypotenuse, you might think we're kind of out of luck here, except there is a third basic trig function that we haven't involved yet, which is the tangent function. And if we remember, SOHCAHTOA, the tangent of an angle is equal to the opposite side over the adjacent side. No hypotenuse needed. So we have this thing. So now we see that tangent of pi over 6 is going to be exactly opposite over adjacent, which is x over 10. And now we have to figure out actually what is the tangent of pi over 6. So we know that for our 30, 60, 90 right triangle, that is very small. For our 30, 60, 90 right triangle, we have an angle of pi over 6, and this one has to be 60. For this triangle, we know that the side length here is given by the cosine of pi over 6. And this length here is given by the sine of pi over 6. So because on the unit circle, the hypotenuse has length 1, the side lengths of the triangle actually coincide with the cosine and sine values, which means when we take the tangent of pi over 6, this is going to be this side length divided by this side length, which is actually going to be sine of pi over 6 over cosine of pi over 6. Because on the unit circle, this side length and cosine of pi over 6 are the same. And same goes for the y value here. We do know what these two values are, right? We know that this is 1/2 and this is root 3/2. So we can plug that in. We get that this has to be 1 over 2 divided by root 3 over 2, which is going to be 2 over root 3 times 1/2, because dividing by a fraction is going to be the same as multiplying by its reciprocal. So the 2's cancel and we get 1 over root 3. So we see that 1 over root 3 is the tan of pi over 6. And we figured that out simply because on the unit circle, the sine and cosine values are the triangle side length values. And so tangent being opposite over adjacent, we have the opposite side, which is sine of pi over 6, divided by the adjacent side, which is cosine of pi over 6. We know what those two values are because we found them geometrically, and we take their ratio and we get 1 over root 3. So now we can use that here. We have that the tangent of pi over 6 is equal to x over 10, which is equal to 1 over root 3. If we multiply both sides of this by 10, we get x equals 10 over root 3. Are we done? Well, the fact I'm asking probably means no, right? This is the value from here to here, right? Because that's where our eyes are, and that's the angle that it forms, and we're 10 feet away, and we found this length. But we have to take our height into account because both us and the cliff start at ground level rather than eye level. So the actual value should be this height plus this length. And this length is, of course, just your height. And in the problem, it's given that you are 1 foot tall. So this is supposed to be 1 plus 10 over root 3. You can simplify that in a number of ways. In the notes I give an approximation, it's about 8.598 feet. Which, of course, the way I've drawn the picture doesn't make much sense, because this is saying that this length is actually less than this one. But that is actually true, I just didn't draw the picture to scale, because this is definitely not 30 degrees. So that's the last problem that we go over in section 4.3. And just so that we have a nice place to stop, I'm going to stop here, although I'm going to pick right back up, but in a different video.